All right, take 11. Hi, I'm here to tell you about our paper, Communicating Natural Programs to Humans and Machines. Let's start with a puzzle. Given the training input-output on the left, can you guess what's in the test output? So what is the green question mark is going to be? So I'll give you some time to look at this puzzle. Okay, so hopefully you're able to guess that the output should be this one. So let's ask a few questions. Can you do this task? Yes, you could do this task. How do you do the task? And what is the mechanism that will allow you to do this task? And further, what does it take to build a computer system that can do the same? So these are more difficult questions, and the ARC dataset by Chalet in 2019 is created to answer these kind of questions. And so here are some more ARC tasks. And so it turns out that humans are very good at ARC, and an average person can solve about 80% of tasks. And it turns out that computers are actually very bad at solving ARC. So the best program synthesis algorithm can only solve 21% of these tasks. So back to our question, what does it take to build a computer system that can solve ARC tasks? Well, clearly humans are very good at solving them, so let's study humans. How do humans do so well on ARC tasks? That's a very difficult question because the thought process is very opaque. So if you give a person an ARC task in isolation and we ask the question, what's happening inside the person's head? We actually can't answer this question. So to answer this question better, we use a communication game to make the process less opaque. So instead of a single person, we use two persons. We have person A and person B. So person A sees the training input-output example and generates a natural language instruction. We call this instruction a natural program. And person B is going to interpret this natural program on the test input to generate the output. And so person B, crucially, can no longer observe the training input-output. And so back to our question, what is happening in person B's head? Well, we can use language as a proxy. So clearly for this task, the person B knows something about a 2x2 color grid and knows about something about replacing the color with another color. We collect a dataset LARC, stand for Language Complete ARC. It is language complete because Human Builder can construct the test output from the language instruction alone. And we use crowdsourcing to collect natural programs for 354 tasks. Let's take a look. So the best way is go on to Google and search for GitHub LARC. And once you're on the GitHub page, you click on the Explorer interface, which will allow you to browse one of the LARC tasks. And so here's the task. So for each task, we have different descriptions, which is the natural program. And so for this description, you could see this is what the person A or the describer is saying. And here are some person B or the builder attempting to reconstruct the test output from the descriptions. To understand how humans communicate using natural programs, we tagged a subset of the phrases in LARC by hand. So the key finding is that natural programs use a large, diverse set of concepts. And the second one is, instead of stating a verbose, precise procedure like computers, natural programs use framing and validation to reduce ambiguity. So here are some charts. The most important one is chart C, where the purple section is procedure. So on average, a natural program only about a third of the time use explicit procedures, and the rest consists of validations and framing to reduce ambiguity. The tagging results, called annotation phrases, CSV, can also be found in the dataset here. Here's some program synthesis results. Because LARC use a diverse set of communication strategies beyond explicit procedures, which is what the computer use, current language-guided synthesis approaches perform poorly. Okay, this is the end. Where to find our paper and dataset? The best way is to go on Google and search for LARC GitHub. All right. All right, we made it. Thanks.